discussed about the full custom and semi-custom and C design flow. Because when you are going for SAR-based ADC, it is a mixed signal design. Okay, mixed signal design in the sense it is going to be going to have a combination of both analog blocks as well as digital blocks. Okay, so before we get into the mixed signal design, it is always better to have an idea of analog IC design flow as well as digital IC design flow. Digital flow you would have already gone through. It was already demonstrated in one of the previous sessions. So I'm taking you all through the analog IC design flow. So followed by that, we'll be entering into the design of SAR-based ADC. Uh, so we started with an example by taking a NAND gate as an example. We completed the schematic capture, transistor level circuit design, and followed by that, we created a top level hierarchy that is a symbol for the NAND gate, which is being used here. And by using that symbol, we have created a test circuit in order to cross-check the functional behavior of the design. Okay, so participants, please keep your mic on mute. In case if you have any queries, you can unmute yourselves and let me know your queries, or you can also share your queries on the chat box. Okay, so let us continue from where we had left. Okay, so for this two input NAND gate, what we have done is uh, we have um, we have created two input stimuli. Okay, using pulse source. Okay, so let us see how to run the simulation. So for running the simulation, I'm going to launch, and that I'll select ADEL. Okay, so here first we should make sure of the simulator. Okay, Spectre is the simulation engine that we are going to use, right? So I'll go into setup, and under that I'll go for simulator or directory or host. So here you can see the simulator at a Spectre. Okay, so no issues there. So I'll select OK, and then I'll go for setup again and go for model libraries. Okay, so it is already fixed for 180 nanometer technology node with the gpdk.ses file. Okay, SES stands for Spectre Circuit Simulator. And then the adjacent column, you have something called stat. Okay, which stands for statistical data. Okay, if you make a double click on that and click on this drop down, then you'll be able to select the processing corners, whether you wanted the analysis to be made on nominal, slow fast, fast slow, or fast processing corners. This will be based on the design specification that you get from the market research analyst. Okay, so let us go with nominal processing corner. So I'll select ENN and click on OK. The next one that we'll have to do is you can see, okay, we have made use of a global voltage source. Okay, so for this we haven't mentioned any value of voltage, right? So what we'll do is we'll enable the stimuli. Okay, enable the stimuli for this. So for that I'll go for setup again and then go for stimuli. Okay, so make a left mouse click on this, and here you can see stimulus type. Okay, this is a global source, right? So I'll enable global source, and you can see it is currently in off state. Okay, your VDD is currently in off state, so you have to enable this. Okay, so click on enable. Okay, and then you mention the function. It is going to make use of a DC voltage source, right? So I'll select the function as DC, and I'll mention the value of voltage. Okay, so let us take the value of voltage as 3 volts. Click on apply. So you can see right now it is in off state, right? So soon as I select apply, it will turn into on state. Okay, and then you can select OK. Now you can select the analysis that you have to make, okay, on this NAND gate, to this NAND gate. So I'll go into analysis and I'll select choose. Okay, so I'll go for a transient analysis. In case of time domain analysis, I'll go for transient. Okay, the stop time I'll select as 100 nanoseconds, and accuracy defaults I'll go for moderate. Okay, so what is meant by accuracy defaults is you have given a pulse, okay, pulse as an input stimuli. Okay, so uh, if you check it for each and every timing instance, you will have discrete samples. Okay, so um, while going for time domain analysis, how many of those samples have to be considered for uh, considered in the design? Okay, considered for analysis. In case if you wanted the result or result to be very accurate, then you can enable conservative. Okay, so that the maximum number of timing instances would be considered for the analysis. And then if you go for moderate, then comparatively less number of timing instances would be considered. And if you select liberal, yeah, comparatively very lesser number, least number of timing instances will be considered for analysis. Okay, so uh, let me go with the moderate. Okay, so I'll select moderate and select OK or apply. Okay, and then in case if you wish to perform DC analysis, then you can enable that and go for save DC operating point. And in case if you wish to sweep some variable, then let us go for component parameter. Okay, so I'll select one of the components from the schematics. So I'll go for select component, and I'll select the first pulse input. Okay, and the parameter that we are going to sweep is DC voltage. So I'll select VDC and select OK. Now go back to the choose analysis option, so you can see the component name and the parameter name. Okay, and I'll sweep the DC voltage from 0 to 3 volts. Okay, sweep type can either be automatic or you can go for linear and mention the step size. I'll go for the step size as 0.001, so you'll get a better curve. Okay, so I'll click on apply and then select OK. Right, now you can choose the outputs to be plotted. Okay, whichever signals you wanted to plot in the graph. Okay, so we can select those things. So for that, what I'll do is I'll go for outputs. Under that, I'll go for setup. Okay, under outputs, I'll go for setup, and everything has to be chosen from the design, right? So I'll go for from design and select the signals to be plotted. So I want to plot this signal A1, B1, and your V out. Okay, I wanted to plot these three signals. Okay, so you can see the setting outputs tab at the bottom. You can select that and click on OK. Right, now you can run the simulation. So you can see the analysis that you are going to perform on the NAND gate and the output signals that you are going to plot. Okay, now to run the simulation, I'll go to simulation option and select netlist and run. Okay, so click on netlist and run. So you can see. Okay, if you right now all the graphs are combined with each other, so I'll select transient analysis. This is what is required for us. So I'll go to new window. Okay, so you are unable to see the signals, right? So it is merged with each other. I'll go for graph and select split all strips. Okay, so you can see all the three signals separately. Okay, so this is the first signal. I can just drag and drop this. Okay, the input signal B1 and the output signal. Okay, so if you wanted to change the properties, so I'll select the signal, make a right click and go for color. If you wanted to change the color, I can go for color And if you wanted to change the style, I'll go for solid. And if you wish to change the thickness, you can go for width and go for thick. Okay, likewise you can change the signal properties for rest of the things. Okay, so I'll go for yellow, style solid, and width thick. The output signal, okay, color I'll go for green. Okay, style solid and width thick. Okay, if you wish to change the background color, you can do that. I'll make a right click on transient response and go for graph properties. Okay, so here you can see background color. Okay, so just make a left mouse click on the color and select any one of the things. So I'll select white color and click on OK and select OK. So you can see this. Okay, now you can cross verify. Okay, for a NAND gate, if both the inputs are at logic 0, then your output is going to be at logic 1. Okay, and if one of the inputs is at a logic 0, sorry, if one of them is at logic 1 and the other one is at logic 0, then the output is obviously going to be logic 1. Okay, the same thing happens here also. If both the inputs are at logic 1, then the output is going to be logic 0. Okay, fine. So we can cross verify your truth table. Okay, so in case if you have any doubts, you can let me know until this point. Okay, so in case if you wish to calculate the uh, delay, okay, so what you can do is you can go for tools, and it can be calculated with respect to any one of the input signal and the output signal. Okay, so what I'll do is I'll go for tools, and under that I can go for calculator. Okay, so in calculator, you can see the keypad, right? So just above the keypad, you can see off, family, wave. Okay, so enable wave because you are going to import all the data from the waveforms. Okay, so I'll enable wave and I'll disable clip. Okay, I'll enable wave and I'll disable clip. And if you come down, you can see function panel. Okay, so from the function panel, I'll select delay. Delay is the function that we are going to choose. And I can close this stack. Okay, so here you can see signal 1, signal 2, threshold value 1, threshold value 2. Okay, and edge number 1, edge number 2. This all these things will depend on which type of propagation delay you are going to calculate. If you are going to check for high to low transition of the output, okay, then which with respect to which signal it has to be done. Okay, and what should be the input and output. Okay, let us see how to do that. So I'll place the cursor in signal 1 and I'll go back to the waveforms. Let me calculate the propagation delay between A1 and the output, V out. Okay, so what I'll do is I'll select signal 1 as A1. Okay, and I'll place the cursor in signal 2, go back to the waveforms and select V out as the second signal. Okay, it is between input and the output. Okay, threshold value, it has to be threshold value. If you consider any type of circuit, okay, then the output voltage swing, okay, should be VDD by 2. Okay, so in case of that, what we'll have to also check out is the switching potential. Okay, in order to calculate or in order to obtain a obtain the switching potential, you have to design an inverter, a CMOS inverter. Okay, so for this, uh, for the specification of NMOS transistors dimensions and PMOS transistors dimensions that we had used. Okay, if you do remember, then during the first session, for the NMOS transistors, the length was 1 micron and width was 5 micron, And for PMOS transistors, the length was 1 micron and width was 10 micron. Okay, so we had already designed a CMOS inverter with these specification, and for that we had got the switching potential as 1.327. Okay, so we'll round it off to 1.35. Okay, so I'll take the threshold value as 1.325 or 1.35. Okay, for both the signals I'll take the threshold value as 1.35. Okay, and in case if we are going to calculate um, the propagation delay between high to low transition. Okay, high to low transition of the output. Okay, and what about the input? It is going to rise and the output is going to fall. Okay, so this is what we'll have to check. Okay, it is going to be between first stage and the first stage. Okay, and edge type 1 is going to be rising. Okay, and edge type 2 is going to be falling. Okay, if we are going to calculate high to low transition, these are the important things that have to be mentioned. Once you have mentioned these parameters, what you can do is you can click on apply. Okay, so whatever parameters were mentioned here will be converted into an equation, and it will get printed in the buffer window. This is the buffer window. Okay, whatever you see here. Okay, once you click on apply and you get the equation, you can click on OK. Right, you can click on OK. Please disable the video. I can see few participants enabling the video in your laptop. Okay, so I can click on OK, and you can see an option. Okay, you can see something called rectangular, and just next to that you can see an option called send buffer expression to ADE outputs. Okay, if you select this, so whatever expression is available over here will get printed in your ADEL window. Okay, so let me show that. So I'll select this option, send buffer expression to ADE outputs. So if I go back to ADEL, then I can get this. Okay, right, so you can change the name also. Okay, so to edit the name, what I'll do is I'll select this, make a right mouse click and go for edit. This is for high to low transition, right? So I'll type the name as TPHL. Okay, for our reference. Okay, and click on OK. Right, so I get this over here. And the same manner, if you wish to calculate the low to high transition. Okay, so I'll again go for delay in function panel, select the signals in the same manner. I'll place the cursor in signal 1, go back to waveforms, select the first signal, place the cursor in signal 2. From the output waveform, I'll select V out. Okay, threshold values are the same, edge number is also the same. So now we are going to calculate the propagation delay for low to high transition. Okay, so if the output is going from low to high, then the input is falling from high to low. Right, input is falling from high to low. So what I'll do is I'll change this edge type 1. Okay, so output is falling, sorry, input is falling and the output is rising. Okay, we can clear the buffer and stack. Okay, in order to remove the previous data. Okay, click on apply, you'll get the equation over here, and click on OK. Now to import this into ADL window, I can select this option, send buffer expression to ADE output. So if you click on this, you'll get it imported in the ADEL window. So you can edit the name of this expression. Okay, so I'll go for edit, and this is low to high transition, right? So I'll type TPHL. Okay, TPHL, and click on OK. Okay, sorry, TPLH. Okay, TPLH and click on OK. Right. Now, if you wish to calculate the average propagation delay, I'll go for outputs. Okay, so I'll go for outputs and select setup. Go for outputs and select setup. And here you can see an option. Okay, first we have to unselect this. Okay, so I'll unselect this and go for outputs. Under that, I'll go for setup, and here you can mention the name. For average propagation delay, I'll mention the name as TPD, and you can give the expression. Okay, so everything is case sensitive, so whatever is mentioned here has to be given over here. Okay, so TPHL plus TPLH divided by 2, close braces, divided by 2. Okay, and click on OK. Right, now what you can do is, instead of you checking out the values over here, okay, in case if you wish to evaluate this, you can go for any one of these two options. Okay, evaluate the buffer and display the results in the table. Okay, so if you click on this, you'll get the value of propagation delay 20.05 nanoseconds, e to the power minus 9 in the sense it is nanoseconds, right? So you can either do this or you can close. Okay, and if you rerun the simulation once again, you can go for simulation and select Northwest Standard. Okay, so the ADEL window itself, you'll get the value of propagation delays. Okay, so TPHL is 20.1363, TPLH is 20.0467, and TPD is 20.0915. Okay, so likewise, you can check the propagation delay between any two signals. Okay, that is between the input signal and the output signal. So any doubts till now, participants? Any doubts till now on how to calculate the propagation delay? Okay, so after simulation, what we can do is we can save this state, because we have to do the post layout simulation, right? We have to import the parasitics. Okay, import the parasitics, and then rerun the simulation for the same set of analysis. Okay, this is what we call as pre-layout simulation, because we haven't completed the layout yet, right? So this is the pre-layout simulation, and you can save the state for in order to repeat the post layout simulation. Okay, so I'll go for session and then go for save state. Okay, so for save state option, I'll enable cell view, because I've done everything for a cell view, right? So I'm running this AC analysis and DC analysis for a cell view. So enable this and select OK. One more thing I wish to add. Okay, so in case if you wish to just a second, let me open the schematic. In case if you wish to print the values of currents and voltages for each and every device in the schematic itself, so what we can do is, the simulation is already run. Okay, so I can peep down as this hierarchy. Okay, so you can make a left mouse click, double click. Okay, and if you select new tab and select OK, then you can see what is there within this symbol. Okay, what constitutes this symbol. Okay, so we can see the transistor level design of a NAND gate. Okay, and if you zoom in, you are able to see the values of width and length. And in case if you wish to print the values of drain current, okay, or your transconductance, or region of operation. Okay, for each and every device you have nearly 90 to 95 parameters. Okay, so let me show that also, and you have two options for that. So first what I'll do is I'll go back to EDVL window. Okay, we have already run a DC analysis. Okay, DC analysis by enabling save DC operating point. So what I'll do is I'll go for results. Okay, and then I'll go for print. Okay, under print I'll select DC operating points. Okay, so I'll select DC operating points, so it will take me back to the schematic. Okay, and I'll select any one of the transistors for which I need all those values. So if you select a transistor, then you get all the values printed over here. Okay, so you can get beta efficient, the device capacitances. Okay, uh, FUG, your transconductance GM. Okay, GM over ID, your drain current ID. Okay, and your source current. Okay, so your region of operation. Okay, the self gain, saturation, VD sat. Okay, and VTH, everything can be checked out for the device. So you have nearly 90 to 95 parameters over here. Okay, so in case if you are interested in printing some important parameters like drain current, transconductance, region of operation, etc., on the schematic itself, then what we can do is you can go for view. Okay, you can go for view, and under that you can select annotations. Okay, and under annotations you can go for setup. Under annotations you can go for setup, and here you can see library. Okay, so all these devices are from GPDK 180, right? So I'll click on this drop down and select GPDK 180, and here you can see cell. Okay, so if you click on this drop down, you can see NMOS and PMOS transistors. So select NMOS. Okay, now you can come down to component parameter. Okay, so make a double click on this component parameter, you can see a drop down. Okay, so if you click on this drop down, you can see DC operating point. So select that, and in case you can just come to ID. Okay, on the right hand side you can see ID, right? So if you click on this drop down, you can make a double click, and if you click on this drop down, you can see all the parameters. Okay, so if you wish to print uh, the drain current ID, so you can select that. Okay, and let width and length be printed. Okay, and you can, if you wish to include some more parameters, then you can again make a left mouse click on component parameter, select DC operating point, and here let me print the transconductance GM, and again I'll click on this component parameter, select DC operating point, and here let me print the region of operation. Okay, and you can click on apply. Okay, so now for if you wish to repeat the same thing for PMOS transistors, again I'll click on this drop down and select PMOS, and I'll make a double click on component parameter and select DC operating point. I'll print the drain current, and then the transconductance, and then the region of operation. So here I'll select region, click on apply and select OK. Okay, so you can enable the supply settings to all and click on OK. So if you zoom in, you can see the values of drain current, your transconductance, and region. Okay, so if you come down, you can see this again for NMOS transistors: drain current, transconductance, and region. Okay, so you can see all these things. Fine. So any doubts till now? Any doubts till now, participants? Okay. So let me move forward. In case if you have any doubts, you can unmute yourselves and let me know your queries, or type your queries on the chat so that it will be taken care of during the QA session. Okay. So let me now uh, move forward to the next stage, which is layout. So I'll check and see this, and I'll close this. Okay, I've already saved the state, so I'll close this. Okay, and then it can so for the layout part, I'll open the transistor level design, which is available within this NAND design. Okay, so I'll open schematic. Okay, I'll open schematic, and from this schematic editor, I'll go for launch and select layout Excel. I'll go for launch and select layout Excel, and I'm going to create a new layout, and the configuration is going to be imported automatically. So I'll select OK over here. Okay, and I'll select OK again. You can see the library, name of the cell, view, and type. Okay, so view and type is going to be layout. So I'll click on OK. So this is because of the package issues, which is not going to impact your layout. So I'll select yes. Okay. So if you see at the bottom, you can see two tabs. Okay, so one is your schematic, and the other one is your layout editor. So you can maximize this, and you can see crosswire. Okay, horizontal and vertical crosswire, just like your basic graph sheet. Okay, x-axis and y-axis in your basic graph sheet, and you can see some bold dots, right? So those indicate major grid, and whatever you see as smaller dots, okay, lighter dots are can be called as minor grids. Okay, so in order to fix this crosswire at the center of your screen, you can use the bind key F. Okay, F stands for fit to screen. Okay, F stands for fit to screen, and then we should import all the devices from the schematic editor, right? So what I'll do is I'll go to connectivity, and then I'll go for generate. Under this, I'll go for all from source. Okay, connectivity, generate all from source. So it'll ask whether all the instances, IO pins, PR boundary, everything has to be imported and generated or not. Okay, so just you can select OK. So now you can see you had two PMOS and two NMOS transistors, right? So I have two PMOS and two NMOS transistors. Okay, and you are able to see only the boxes. You are unable to see the terminals, right? So in order to visualize the terminals, I'll go to Shift F. Okay, so in your PMOS and NMOS transistors, you in your MOSFETs, obviously. Okay, in your MOSFETs, you have four terminals, right? You have four terminals. So So in a MOSFETs, you have four terminals: gate, drain, source, and bulk. Okay, the drain and source are interchangeable because they are of same dimensions, and they are interchangeable. Okay, and then if you zoom in, you can see only three terminals. Okay, whatever you can see at the center is the polysilicon, which is obviously the gate terminal, and on either side you can see drain and source terminal. That's it. Okay, but you are unable to see the bulk. So to visualize the bulk terminal, what you can do is you can select the transistor, go to its properties, okay, by using the bind key Q, or what you can do is you can make a right click and choose properties. Okay, so here you can see under attributes you can see the name of the technology node, the cell name, view name. Okay, and then you can see a tab called parameter. Okay, so you can select parameter and then you can go through the dimensions. Okay, so if you come down you can see body type. Okay, if you click on this drop down you can select integrated or detached. Okay, so here the drain and bulk, sorry, source and bulk are tied to VDD. Okay, in terms of PMOS transistor, and in NMOS transistor, in the NMOS transistor, where the drain terminal is connected to the output, the source is connected to the next one, next NMOS transistor, which is placed down, and for the transistor that is placed close to the ground terminal, okay, both source and bulk are connected to the VSS. Okay, so for PMOS transistor, I'll go for integrated bulk. Okay, I'll choose integrated. You can see left tap and right tap, okay, which indicates whether you want the uh, uh, bulk terminal to be on the left hand side of the transistor or on the right hand side of the transistor. Okay, so let me go with the left tap itself, click on apply and then select OK. Now you can see source and bulk are integrated with each other. Okay, in the same manner I'll select this PMOS transistor also, go to its properties, and body type I'll select this as integrated itself, click on apply and then select OK. Okay, fine. Now you can see the NMOS transistors. Okay, so the output of the drain of this NMOS transistor is uh, getting connected to the output, whereas the source of this transistor is getting connected to the drain of this transistor, this NMOS transistor. Okay, so here it will be better if we have a detached bulk. Okay, so let me show how to get that, or how um, how can we see a detached bulb? How is it different? Okay, so I'll select this transistor, go to its properties. Sorry, I select this transistor, go to its properties, and in parameter under body type, I'll go for detached. Okay, so click on apply and select OK. So now you can see this is how it looks like. Both the source and bulk are separated from each other. Okay, so this can be decided whether we have to go with integrated bulk or attached bulk. We can decide it based on the circuit complexity. Okay, it is not like we have to go only with the integrated bulk or we have to go only with the detached bulk. It is up to the designer to decide. Okay, and then you can see the last transistor which is connected to which is getting connected to uh, the ground. Source and bulk are getting connected to the ground, so it is okay if we have an integrated bulk. So I'll select this, go to its properties, and under body type I'll go for integrated, apply, okay. So now you can see this is the difference. This is a detached bulk, this is an integrated bulk. Okay, so now uh, you can also see the pins. We have seen the devices. Okay, you can also see the pins if you scroll down, zoom in. Use your mouse scroller to zoom in and zoom out. So you can see the VSS over here. On the right hand side, you can see the output pin. On the left hand side, you can see pin A, and on top, you can see your second input and the VDD. It is not like you have to you have to connect the pins from wherever they are. Okay, you can place it as per our convenience. Okay, pins can be placed as per our convenience, and You can see a blue colored box surrounding all the MOSFETs and the pins, right? Okay, so this blue colored box is called the PR boundary. Okay, your placement and the routing boundary. Okay, this blue colored box is called the placement and routing boundary. Okay, so you can expand or contract your PR boundary. Okay, in case if you wish to expand, okay, you can make use of the shift option. Okay, so for shifting the PR boundary, the bind key, okay, is yes. Okay, click on yes in the keyboard, take your mouse pointer close to any one of the PR boundary. So if I wish to expand this or shift this, I'll make a left mouse click to select this and use the mouse or upward downward arrow. Okay, like this. Okay, use the mouse or left upward downward arrow to replace this. Okay, and I can also rearrange the components. So if you wish to align the components. Okay, so for example, here we have the second input, right? So if I wanted to align this to the right hand side PR boundary, so the process for that is abutting. Process is called abutting. So for that, I'll use the bind key A. Okay, click on A and zoom in and select one of the boundaries on the pin. Okay, so select this boundary. Okay, this has to be aligned with this boundary of the PR. Okay, this PR boundary, right? So I'll make a left mouse click over here, so it gets aligned with this PR boundary. Okay, you need not drag and drop, and you need not zoom in and place this carefully. No, not required. Okay, so next is you can also rearrange your MOSFETs. Okay, so I'll select these two. Okay, select both the transistors and we can drag to the top. Okay, and then you can rearrange this VDD. Okay, VDD has to be abutted to the top here to this. Okay, so I'll click over here so you can see VDD is getting aligned to this. Okay, so whichever devices and whichever pins are present within the PR boundary only will be fabricated. Okay, in case if you wish to have an outline of the interconnections, okay, just to make sure that you don't miss anything, I'll select the entire layout by using Control A. I'll select the entire layout. Now I go for connectivity. Then I'll go for incomplete nets. Under that, I'll go for show or hide selected. Okay. Select the entire layout, connectivity, incomplete nets, and we can go for show or hide selected. So you can see all the missing connections. Okay, you can see all the missing connections over here. Okay, in case if you wish to expand the PR boundary further, you can do it. Or if area is the main constraint, okay, then we can also work on that. Okay, so right now I am taking you through a beginner level of layout design. Okay, once you are very comfortable with this, you can move into reducing the space. Okay, and for that you have different techniques like source sharing, okay, or abutting, making use of fingers, multipliers, etc. You can work on those things. Okay, so let me show that. Okay, so let me go to let me show you by shifting the PR boundary, expanding it further. Okay, so I'll go for yes, select the top boundary and I'll fix it over here. And similarly, I'll align the top surface of VDD to the PR. Okay, and then I'll rearrange these two PMOS transistors. You can also bring them close to each other. Okay, and bring them close to each other. So I'll have them over here. Okay, and then move this NMOS transistors. Just you have to select this, click and drag. Okay, so you can move this NMOS transistor, and the source of this NMOS transistor is getting connected to drain of this NMOS transistor, right? So I can move this slightly to the top, and you can also align this with that. Okay, so I'll go for abutting. So this transistor, this surface has to be aligned with this. Okay, done. Now let us do the connections. The main things are drain of these two transistors have to be connected. So I'll go for P, shortcut P. Okay. So at the schematic level, transistor level schematic, you were using wires. Okay. But here they are called path segments. Okay. So I'll start the connection from here. Okay. And I'll take it to this. Okay. So drain of this NMOS transistor have to be connected to this output. Okay, and this pin has to be connected to the output. Okay, so I'll start the connection from here, and I'll complete this. Okay, if you make a double mouse click, it will get completed. So you can align this. Okay, align this with the output pin. This is your input. You can use the abutting option. Okay, so I'll make use of abutting option. The top surface of this output pin has to be aligned with this. Okay, and then we'll go for path segment again. The source of this NMOS is getting connected to drain of this NMOS. Okay, and hereafter we are left with sorry, before that, at least help me move this transistor step. And then let's go for okay, and now we are left out with the connections between input pin, okay, input pins and VDD VSS. Okay, you can also shrink the PR boundary slightly towards the right hand side because you have this much of unwanted space, right? So you can reduce this. Okay, so for that you can first remove this output connection. Okay, and then you can go for shift. Okay, and I'll take this to the right. Okay, so now you have reduced considerable amount of area. Okay, and I'll take this output pin. I'll abut this output pin with the PR boundary. Sorry, second input. Okay, this is your output with PR boundary. Okay, so we can also redo the connection. So I'll remove this, or you can connect it here itself. So I'll go for path. So from here I'll start and complete this. and here I start this. Okay, and from the output pin I can start the. Okay, so it is done. The next thing is your input pins. Okay, so now till now we have been working on connections that are with the same layers, that is only metal one. Okay, now you can see. Okay, this is a metal and it has to be connected to polysilicon. Okay, so for this we need wire. Okay, because you are trying to connect two different layers. Okay, for example, just imagine a plumber. Okay, if he is trying to connect two pipes of different diameter. Okay, then he will make use of a small device called coupler. Okay, so likewise you'll make use of a wire over here. Okay, so what I'll do is I'll start the connection from here, from the input pin A. Okay, drag it to a certain distance. Okay, and then I'll make a right click. Okay, and go for wire down to select poly. Okay, because we are going to connect it to a polysilicon, right? So I'll select poly and you can get a wire like this. Now you are free to place this wherever you want. Okay, so I'll place this over here and then drag. Okay, and again if you make a left mouse click you can complete the connection, and this is for pin. Okay, and in the same manner I'll do the connection for pin B also. Okay, so when it comes to layers, we have to uh, try and avoid polysilicon as much as possible, because polysilicon is a highly resistive material and it is also the costliest material. So using more amount of polysilicon will make your layout costlier. Okay, polysilicon is the highly resistive material and it is also costliest material. Okay, so using more number of polysilicon connections or using more amount of polysilicon in your layout makes it costliest affair. Okay, just a second, participants. Sorry for the interruption. Okay, so let us continue. So you have the second input pin over here. Okay, um, so you can rearrange this and bring this downwards. Okay, or you can start it from here. You can also start from here. Okay, so I'll go for a button. Okay, I'll take this to the other side. Okay, and I'll start the interconnection from here. Okay, for path, start my connection, drag it to a certain distance and go for wire down to select poly. Okay, I'm free to place wherever I want. and I'll complete the connection over here. And then this also has to be taken to the NMOS transistor, sorry, PMOS transistor. So what I can do is, I need to cross over anyway. I cannot cross over with metal one itself. Okay, so I can cross over. Okay, and I can drag it to a certain distance. Okay, in case if you are trying to reduce the amount of polysilicon, what we can do is, you can make a right click, go for wire down to metal one. Okay, start the connection. Okay, and then you can come back to wire down to poly. Okay, you can place it over here and complete the connection. Okay, so you have avoided so much of polysilicon over here, but on the other side you have included two wires. Okay, so including wires will give rise to parasitic capacitance, because as I have told you, this via is between a metal and a polysilicon. Obviously both are conducting material. At one, metal is obviously a conductor, whereas polysilicon is will be able to conduct at a certain threshold value. Okay, so you have two layers over here, and they are connected with the contact. Okay, and they will be separated by an insulating material. Okay, so what is the definition? Two conductors are separated by an insulating material that forms a capacitance. That is the definition of a capacitance, right? So if you have more number of wires, then you have more, then it gives rise to parasitic capacitances. So you have to plan the layout in such a manner that everything is fine in the design. Okay, and now let us go for VDD and VSS. Okay, so till now you know like how to you should be having an idea of how to do the connection between a pin. Okay, a pin and a terminal, right? So now what you can do is, you can take the entire top layer to be VDD and the entire bottom layer to be VSS. Let us see how to do that. Okay, so for that what I'll do is, I'll go to place. Under that I'll go for pin placement. Okay, so here on top I need the VDD, right? So I'll select VDD. Under edge I'll go for top. Okay, click on apply and select H-ray. Similarly, I'll select VSS. Under edge, I'll go for bottom, click on apply and then select H-ray. Okay, so if we close, we can see the entire bottom layer is now VSS and the entire top layer is now VDD. Okay, so now you can complete the connection. Okay, so from the PMOS transistor, you can connect it to VDD, and from NMOS transistors you can connect it to VSS. So you can connect like this, and you can also connect like this. So I'll start the connection from here. Okay, and complete it like this, or I can connect it like this also. Connect it to the source over here. Anyway, that is getting connected to VSS, right? So no issues. Okay, so here there is no proper alignment. So again I'll go for abutting and align this with the source of the transistor. Okay, So your layout is now complete. Okay, so now what I can do is I can save the layout. Okay, I'll save this layout. Now we'll have to go for physical verification process. Okay, so what I'll do is I'll go for Ashira. Okay, under Ashira I'll go for technology. Okay, it's because you need some library file which will translate the layout and compare it with the design rules. Okay, so I'll go for this browse option. Okay, single dot is for present working directory, double dot is to go back to previous directories. So I'll use this double dot and go back to the previous directory. Okay, so I'll select home. Okay, and then I can go for CAD. Okay, and then Foundry. Okay, and I'm working on an analog design field, right? So I'll go open analog. I'm working with 180 nanometer technology node. So I'll open that and I'll select this library, Ashura underscore tech.lib. Okay, so I'll select OK now. Now we can start with the physical verification DRC. Okay, so I'll go for Ashura again and we can see run DRC option. Okay, so go for run DRC. On the first line, you can see the layout design source. Okay, so library is one underscore Konganadu, which is the same thing. Cell name is 9 underscore design and field name is layout. So everything is fine. Okay, and I can give a run name. I'll give the run name as NAND underscore DRC. And if you come down, you can see an option called technology. Okay, so click on this drop down and select CPDK 180 and select OK. If you wish to check what is happening in background, you were able to see an option called watch log file, right? So you can select that. Okay, so if you click on yes, you can see the results. So your layout is DRC free. Okay, DRC clean. Okay, so you can click on close. Now you can go for Ashira. Okay, next one is LBS, right? So I'll go for run LBS. Okay, so in the first line you can see the schematic design source. So it is nothing but comparison between schematic and layout, right? So in the first line you can see the schematic design source where you can see the library name, cell name and view name, and the layout design source where library, cell and view can be seen. Okay, give a run name. Okay, which is NAND underscore LBS and technology is GPDK 180, right? Select OK. Click on watchdog file to see what is happening in the background. Okay, so you can see zero net mismatches, zero device mismatches, zero pin mismatches, zero parameter mismatches. DRC violations is also zero. So if we click on yes, we'll be able to see the result. So at the bottom, you can see the result schematic and layout match. Okay, so we can close this. Okay, and now we can go for parasitic extraction. Okay, so for that I can go for Ashira. Under that I can go for run Qantas QRC. Okay, select run Qantas QRC, and if you scroll up, you can see the setup tab. Okay, you can see the setup tab, and you can see the technology GPDK 180. If you come down, you can see output, right? So if you click on this drop down, you can go for extracted view. Okay, and now come to the next tab, extraction. So you can decide upon which devices have to be extracted, or whether you want only the resistances, or you need only the capacitances, or you need both resistance and capacitance. Okay, so you can click on this drop down and you can select RC. RLC and RLCK is not possible because you don't have you have not designed an RF circuit. Okay, so RLC, where L is an inductor, RLCK, K is the mutual inductance. Okay, so I'll select RC, and reference node I'll mention it as VDD. Okay, and then you can go for net listing. Okay, and select do not include model for the first four options because we don't have the model files for GPDKs. Okay, so I'll go for do not include, do not include. Okay, and select OK. Click on notes log file. So you can see the result. Contest QRC run man underscore LBS completed successfully, and the output is in the library name, cell name, and view name is given. So you can go back to the library manager. Okay, and you can check on underscore Kongamadu. Okay, cell name NAND underscore design, and view name EB underscore extracted. So I'll select this. Okay, I'll close this and I'll open this. So if you zoom in, okay, you can see P resistor. Here you can see P capacitor. Okay, so if you click on Shift F, and if you zoom in further, you can see the values. So it is 661.966 A. A stands for attofarad. Okay, and if you zoom in further, here you have one more capacitance. So here you have a resistance. So here you can see 350 milliohm. Okay, like this. Okay, so parasitic extraction is done. So I close this. Okay, and now we'll have to go for back annotation process. Okay, so for back annotation in the sense, I need to import the parasitic resistances and the capacitances from this AV extracted view into this test circuit. Okay, so I'll select this test circuit and select the view as a schematic. Okay, now I'll go back to file, new, and select cell view. Okay, so here I'll have to select the type as config. Okay, so I'll select the type as config and click on OK. Right, so here I'll have to go for use template. Okay, so the template name has to be the name of simulator with which we had simulated the design earlier. So that was Spectre, right? So I'll select Spectre and click on OK. Now you can see the view option. Okay, so if I go for the view option, I'll go for schematic. Okay, select OK. So you can see table view and tool view both are same. Okay, both gives you the uh, name of the cell, name of the library, and the type of view form. Okay, both instances. So here you can see an option called I0. Okay, I0 is the instance number of the NAND gates symbol that we had created. So if you expand that, you can see two NMOS transistors and two PMOS transistors. Okay, so I'll select this instance I0, make a right click, go for set instance view, and select AV underscore extractor. So all the parasitic resistances and capacitances are imported over here. Okay, so save this configuration and select open. This should bring back your test circuit. You should not have it open already and say we have got it. Okay, after creating the configuration, you should open the you should from the hierarchy editor you should open the test circuit. Okay, and to confirm whether the parasitic resistances and capacitances are imported or not, we can just peek down this hierarchy. Okay, so I'll go for a double click, go for new tab, click on yes, so you can see the device capacitances and resistances. Okay, so all the parasitic resistances and capacitances are imported, so you can run the simulation. I'll go for launch, select 18EL. Okay, load the state. Okay, so I'll go for session and select load state. We have already saved the state, right? So I'll load it back. Okay, rerun the simulation. Okay, so you can see the impact. So average propagation delay was 20.09 earlier, 0.9 nanosecond, but here it is 20.12 nanoseconds. So there is no much of difference. Okay, so I think we are good to go. Okay, in case if the difference is too much, then we'll have to rework on the design. Okay, so I'll close this, and the final step is generating the GDS file. Okay, so let me show that. So to generate the GDS file, I'll also post this node in transistor level design. Okay, so to generate the GDS file, I'll go back to the command interpreter window, and from here I'll go to File, Export, okay, and select Stream. Okay, under File, select Export and select Stream. Okay, so this is the GDS file is also called as stream out file. Okay, that is why we are selecting stream. Okay, and here you can see stream file, library, top cell, view, and technology library. Okay, stream file in the sense you can give any name for your GDS file. Okay, but it has to be it should have an extension .gds. Okay, and then you have to select the library and top cell which has the layout. Okay, so what I do is, next to library I have the browse option, right? So I'll click on this browse option and select the library, select the cell which has the layout, and select the view as layout. Okay, so click on OK. You can see the name of stream file with an extension .gds. You can also give a different name, but extension should be .gds. And then you can see technology library. If you click on this drop down, you can select GPDK 180, okay, and select translate. Okay, so you can see translation completed, zero errors and zero warnings found. Okay, so you can only view the log file because GDS file will be a binary file. Okay, and you can go back to your workspace which is there at the desktop. Okay, now, right? So if you open this, you can see the GDS file generated. Okay, so and you can see the name in man_design.gds. Okay, so design.gds. Okay, so if you try to open this, it will show. Okay, we have a separate tool for extracting the contents. Okay, so right now we don't have it. It will be there with the foundry. Okay, so if you will be sending this GDS file to take out your design, so the foundry people in foundry will have a separate tool to extract the GDS file, extract the contents of the GDS file. Okay, and uh, they'll extract the and they'll start taking out your data. Okay, so if you scroll down, you can see the layer map file, your technology library, and then you can see the contents of your layer. Okay, so close this. Now let us see. We have created an AND gate. Okay, so if you are trying to hmm, if you're trying to create an AND gate, so what you need an AND design with an inverter, right? So that will be mixed signal design. Okay, So what I'm going to do for demonstrating the mixed signal design is, we have a NAND gate. Okay, I'll create an inverter, okay, using Verilog. Okay, and I'll import that into Virtuoso. Okay, create a schematic by combining the transistor level design. Okay, NAND's transistor level design and the symbol of an AND gate. Okay, and then demonstrate the simulation, demonstrate how to do the simulation. Okay, so from the workspace, okay, Tamil Nadu, what I'll do is, I'll open a terminal and I'll create a .v file. For that, I need a text editor. Okay, so I'll make use of gedit, which is the most basic text editors, and I'll type the file name inverter.v. Okay, and click on enter. So you can create the design. So I'll create a new module with the name IMV, and within braces I'll mention the input and output port. Okay, I'll assign the input port. Okay, and I'll assign y as the output port. Okay, now the operator, assign y is equal to negation of a. Okay, and I'll end module. Okay, I'll save this and I close this. Now we have to import this .v file into Virtuoso. Okay, so let us see how to do that. I'll go back to the command interpreter window. Okay, so from the command interpreter window, what I'll do is, I'll go for file and then I'll go for import. I'm going to import a Verilog file, right? Verilog program. So under import, I'll choose Verilog. Okay, so here you can see Verilog files to import, right? So I'll go for this browse option and select the .v file. Okay, inverter.v, click on open, and then the target library name, to which library it has to be imported. So I'll go for browse and I'll select one underscore terminal. Okay, click on close. Right, now I need to import the functional view and symbol for this design. It has to be made use of in the schematic, and I need to generate a netlist also, because I am creating a schematic, right, combining analog and digital blocks. Okay, so I'll select OK. So now if you see this Verilog import completed, look at the log file, okay, for process execution details. If you click on yes, okay, so you can see using ncvlog, okay, using ncvlog binary for compilation. As I have told you already, all the tools that are there in Cadence are interoperable. Okay, so a Verilog compiler is used for compilation. Okay, to compile the .v file. Okay, and then you had created a symbol. Okay, and you had created a functional view. Okay, so that is what you can see. We had created a symbol and we had created a functional view. Now let us go back to the library manager. So it is not yet updated. Okay, so I'll select it once again. Now you can see INV is the cell that is imported, and we have a functional view. If you make a double click on this, then you can see the program, and if you make a double click on this symbol, you can see the symbol. Okay, now combining these two, okay, the NAND transistor level design and the inverter, okay, created using a .v file, I'm going to create an AND gate. Okay, so I'll create a new cell, file new and cell view. Okay, I'll name the cell as and underscore design, and the type is going to be schematic. Okay, I'm going to create a schematic. Click on OK. Okay, now instantiate the NAND gate from 1 underscore 24. From NAND design, I'll import its symbol, instantiate its symbol. The output of this NAND gate is getting connected to the input of AND gate. Okay, so I click on add instance. I'll get the inverter symbol from INV. Click on hide and I'll get it. Okay, now we need an output port. Okay, so I'll go for add pin, name of the output port as and out. Click on hide and place it, and then I need a ground terminal. I'll get it from the lib. Okay, so I'll have it over here. Then I need a DC voltage source, VDC. Input voltage I'll take as a 3 volt, sorry, supply voltage. Then I need a pulse stimuli, V pulse. Okay, so voltage 1 is 0 volt, voltage 2 let me take as 3 volt, and period let me take 20 nano, delay time 10 nano, rise time 1 pico, fall time 1 pico, and pulse width 10 nano. Okay, click on hide and I'll have it. And then one more V pulse source. Voltage 1 is 0, voltage 2 is 3. Period let me take as 40 nanosecond, delay 20 nano, rise time 1 pico, fall time 1 pico, and pulse width 20 nano. Click on hide and I'll place it. I need ground terminal for all these things, so I'll copy this. Okay, so you should be knowing how to copy. Okay, and I'll do the connections. Okay, so I'll use wire, complete this. The output of NAND gate is connected to input of inverter. VSS is connected to ground. From VDD, I'll take a wire, and from input I'll take a wire. From input V, again a wire. Okay, and then from VDD, I'll take a wire like this. Okay, now let us complete the connection using gate. VDD, twice A in, B in, and B in. Okay, so click on hide, VDD over here, VDD over here, A in, B in, B in, and B in. Okay, you can give one more label, soft and underscore. Click on hide and I place it over here. Okay, so this is the schematic mixed signal, schematic of a mixed signal design. Okay, so I'll go for check and save, and I'll go for command interpreter window. I don't have any errors or warnings. Okay, and I'll close this. To simulate this mixed signal design, I have to create a config view. Okay, so for that, I'll select this and the design. Okay, select the view as a schematic. Now again I'll go back to file, new, cell view, okay, and the type is going to be config. Okay, so I'll go for config and select OK, right? So now under use template, I'll have to select the template name as the simulation engine that is going to be used, right? So I'll select the AMS simulator and click on OK. The top cell view is going to be schematic again. Click on OK, and I'll have to update this view. Okay, so I'll go for view and select update. Okay, and I'll save it once again and click on open. This should bring back my and schematic. Okay, so click on open, so it will bring back my and schematic. Now let us run the simulation. So I'll go for launch and select ADEL. Okay, so go for setup. Make sure of the simulator, it is not Spectre, it is AMS. Okay, so simulator is AMS, so select OK. Then go for setup, model libraries. So we are working on 180 nanometer, right? So I'll disable all the other technology nodes. So here under this section, I'll select the nominal corner, click on apply and select OK. And let us go for analysis. So I'll run just a time domain analysis where the stop time is 100 nanoseconds. Sorry, it is small again. Okay, accuracy default, I'll go for moderate. Click on OK. I'll go for outputs, setup. I'll select the signals to be plotted. I'll select both the input signals, output of the NAND gate and output of the AND gate. Okay, now I'll select OK and run the simulation. Go for simulation, netlist and run. Okay, so I'll show you what is there in the background also. Right now we will not be able to understand. Okay, so now you can see. Right now everything are merged with each other, so I'll go for graph, split all strips. Okay, input of Agin, input Bn, output of the NAND gate, and the output of AND gate. Okay, so here you can see only in zeros and ones because it is a digital block, right? In a digital block, you'll have outputs only in form of zeros and ones. Okay, that is why you are able to see it as zeros and ones. Okay, and if you check at the log file, okay, you can see the interoperability of Cadence tools. Okay, so you can see IRUN is the simulator, okay, that is getting initialized even before the simulation starts. The design is getting compiled once again. Okay, it is elaborated and then using Spectre solver with the arguments. Okay, here in Cadence virtual Spectre circuit simulator. Okay, it is getting mapped. Okay, and then it starts running the simulation. Okay, so NCSIM is also being called up. Okay, and then you get the result of transient analysis. Okay, so this is about the mixed signal design and simulation. Okay, now let us move into the topic that we are about to discuss. Okay, so let me save the state as cell view. Okay, just a second. So screen share. Okay, so we have gone through the analog pre-custom IC design flow and the mixed signal design flow. Okay, so now let us go into the topic SAR ADC. Okay, so SAR in the sense it is successive approximation register. Okay, as we move on, we'll check out the backgrounder also. Right from backgrounder we'll go. Okay, so analog to digital converter, we are using that as a data converter, which converts a continuous analog waveform into discrete digital representation using a binary search algorithm. Okay, so what is the principle used by this data converter is, as we have seen, this binary search algorithm, and the objective is to, for example, let us determine an unknown weight by a minimal sequence of weighing operation, and this is a solution to many of the mathematical puzzle which dates back to 1500s. Okay, it is a simple example. Let me show you. Okay, just imagine. So you can, you have everybody would have come across a fruit vendor or vegetable vendor who comes on the street. Okay, so he'll be having a weighing balance. On one side, he'll keep on adding weights, and on the other side, he'll have the vegetables or fruits. Okay, for which he is about to measure the weight. Okay, so likewise we are going to, that is what we are going to repeat here. Okay, in the successive approximation register. Okay, we are going to measure an unknown weight. For example, it is 45 kg. Let us assume the unknown weight to be 45 kg. Okay, and we have the weights available, like 1, 2, 4, 8, 16, and 32 kgs. Okay, these are the weights available. So what we'll do first, on the right hand side we have the unknown weight. Okay, and on the left hand side we'll keep on adding the weights. We'll start with the highest one. Okay, which is 32 kg. Okay, so 32 kg is less than the unknown weight, right? So the MSB will be set to 1. Okay, MSB will be set to 1. Now you start including the next possible weight. Okay, after 32 you have 16 kg. So along with 32 kg you will also include 16 kg. So 32 plus 16, it is 48, right? So what happens, it gets, on the left hand side it slants down, while on the right hand side it comes up. Okay, so what we'll do, the output is going to be 0. So uh, the unknown weight is slightly higher. Okay, so the 16 kg weight is rejected, so we'll remove that. After removing 16 kg, we will go for the next highest possible weight, which is 8 kg. Okay, so 32 will be, sorry, 8 kg will be added along with 32 kg. Okay, so 32 plus 8 is now 40 kg. Okay, which is less than the unknown weight. So that will be retained, and we'll have a 1 over there, binary 1 over there. Okay, and then we'll include the next possible weight. After 8 kg we have 4 kg. Okay, so 32 plus 8 plus 4, we have 44. Okay, which is again less than the unknown weight. Okay, so we'll have a binary 1. The bit will be set to 1. Okay, and now we'll include the next possible weight. Okay, which is 2 kg. So along with 32, 8, and 4, we'll include 2 kg also. Okay, so the weight now becomes 46, which is greater than the unknown weight. So that will be rejected. We remove the 2 kg, and finally we'll include the 1 kg weight. Okay, so now it will be a perfect balance, right? So this is how we are going to do it. If you are working on a 4-bit ADC, okay, 4-bit ADC based on successive approximation register, the MSB will be set to 1 first. Okay, MSB will be initially set to 1, and the particular value of voltage will be compared to the analog voltage. Okay, so if it is less, okay, if if the value of voltage sent from the successive approximation register is less, then the bit will be set bit, bit will still remain at 1, and the next significant bit will be set to 1. Okay, and if it is greater, then the MSB will be set to 0, and the next significant bit will be set to 1. Okay, again it will go to compare. Okay, this is what will be happening until all the uh, 4 bits are getting filled up, until all the 4 bits will get filled up. Okay, this is the principle. Okay, and for doing this, we have a functional block diagram. Okay, we have a sample and hold circuit, we have a comparator, we have a digital to analog converter, and we have a successive approximation register along with the timing module. Okay, so for this timing module, we have a start conversion and end of conversion. Along with that, we'll also have a data busy. Okay, data ready or data busy. So what is the functionality of each and every block that is available over here? The sample and hold circuit is used to acquire the input voltage. Okay, the comparator is to compare the input voltage to the output of DAC, digital to analog converter, and it sends the data back to successive approximation register. Okay, so successive approximation register to supply an approximate digital code of input voltage. Okay, the successive approximation register is mainly to uh, supply an approximate digital code of input voltage to the internal digital to analog converter. So for whatever output we get from the comparator, we need a digital code. Okay, so successive approximation register generates that digital. Okay, and finally, we have the to our DAC for comparison with reference voltage. And this supplies the comparator with analog voltage equal to the digital code of the SAR, successive approximation register. Okay, so now we uh, we have already seen how it works. The MSB of SAR is initialized to a digital 1, and the code is fed to DAC. Okay, the DAC supplies an analog equivalent to the comparator. If the voltage exceeds the input voltage, then comparator causes SAR to reset the bit, or it is left as 1. Okay, and the next lower significant bit is set to 1. This happens until all the 4 bits are either set or reset. Okay, so we are going to design this 8-bit SAR ADC using discrete ICs. Okay, and why we go for the discrete ICs? Okay, it is because in the ORCAD space we have all the blocks readily available. Okay, so we are going to design, capture, and simulate the design using ORCAD space, which is also a good system design example for lab experiment. Okay, so what we'll do is we'll design and illustrate each and every block separately. Okay, your DAC, R2 to R ladder, successive approximation register using D flops, comparator, sample and hold, and finally we'll integrate all the blocks together and check for the function and go for the functional verification of the design by simulation. Okay, so what is an R2 to R DAC? Okay, let us check that. So it is a data converter which uses two precision registers resistors to convert digital binary number into analog output. Okay, and it is also a ladder network. So what is a ladder network? It uses two resistance values, one with the base value and the other one twice the value of base value. Okay, so the ladder network looks like this. Okay, this is a 4-bit ladder network where the voltages will be applied to this arm. Okay, you can see VA, VB, VC and VD. Okay, VD will be the most significant bit. Okay, the output will be fed to the amplifier, okay, or the comparator circuit. Okay, so the main principle is, if you look at from this side or this side, the equivalent resistance should be 2R. Okay, that is the main principle. Okay, so it is all about connecting the resistors in parallel and series combination. If all the binary inputs are grounded, if all these inputs are grounded, like we have seen VA, VB, VC and VD, right? Okay, so if all of them are grounded, then the bits are 0, 0, 0, 0. Okay, we have indeed an equivalent resistance of 2R. Okay, and finally you get the equivalent resistance. Okay, you have to reduce, okay, figure out the equivalent resistance for each and every combination. Okay, and finally arrive at this part. Okay, you'll have a single resistance and the output voltage is 0 over here. Okay, and therefore all the four bits are 0. Okay, similarly, if there is supply voltage applied to any one of the arms or all the arms, how does it look like? Okay, for each and every sequence, you have to um, uh, calculate the equivalent resistance and figure out the output voltage at this node. Okay, so if you have the voltage connected at the LSB, then the output voltage will be 1/16th of the input voltage. If it is connected to the next one of the LSB, then the output voltage will be 1/8th of the input voltage. If it is connected to the if the voltage is connected to the bit that is just closer to the MSB, then the output voltage will be 1/4 of the input voltage. And if it is connected to the MSB, then the output voltage will be half that of the input voltage. Okay, so this is how it works. And for different combinations of input voltage, we have got the output voltage of the RT2R ladder network. So this is for a 4-bit ladder network. Similarly, if you are expanding it for an 8-bit, then you can see the formula. Okay, like this, you can expand it for 16-bit or 32-bit also. Okay, so um, we have also designed the 8-bit R2 2R ladder network on RCAD PSpice, and this is the circuit. Okay, screenshot of the circuit. Anyway, I'll be showing it on the tool also. Okay, so let us jump into the tool. Okay, so because of timing constraints, I have already captured the schematic. Okay, so you can see this is an analog switch. Okay, and for that I have used the IC number ADG413B. Okay, so you can get all the ICs from this place part. Okay, you can get it from here. Okay, and in case if you don't have an idea whether it is present or not, then what you can do is you can check for that in pspice.com. Okay, you can visit the website pspice.com, and here in this website you can check for the available parts. Okay, so you can go for products and solutions, sorry, pspice models. Okay, you can go for pspice models, and here you can search. Okay, switch. Okay, you can search as a switch, or you can mention this IC number. Okay, ADG413B. Okay, You can mention ADG 45413B. ADG 413. If you click on enter, then it will give you the solution. So here you can see ADG 413B precision quad SPST switch, or you have ADG 413T/AD precision quad SPST switch. Okay, so you can cross verify whichever part is available or not from pspice.com website. Okay, you can go to pspice models and you can type the part required. Okay, you can get the data sheet on Google also. So if you copy this part number and paste it on Google and search for data sheet. Okay, you can get it from analog devices or any other manufacturer like Texas Instruments, Motorola, etc. Okay, so you can go through the schematic. Okay, and you can also go through the other uh, parameters of the switch. Okay, so for example, you can see the value of supply voltage. It is 15 volt. Okay, so 15 volt supply voltage has to be given and ground has to be 0. Okay, or PSS in the sense it has to be minus 15 volt. So it is a dual supply. Okay, so you can see dual supply. Okay, likewise you can check all the parameters over here. Okay, similarly I have made use of an inverter. Okay, and then this is the ladder network for an 8-bit DAC. Okay, so I have given 8 inputs. Okay, so this is an 8-bit DAC. The output of this DAC is sent to a comparator circuit. Okay, in short, it is an amplifier. Okay, so we have got this as a R2R ladder network, and then you have the SAR logic. Okay, the successive approximation register using the D flip-flop. Okay, successive approximation register using D flip-flop. Okay, is the schematic, and then you can see comparator. Okay, this is the uh, comparator circuit, and this is the sample and hold circuit. Sample and hold, as we all know, is to capture the input. Okay, capture the input voltage, analog voltage, and the output of the sample and hold network will be sent to the sent as the input to the comparator. Okay, the output of comparator will be sent to the successive approximation register. So here we have the overall circuit. Okay, so we have the comparator over here. Okay, and then we have the SAR logic. We have created it as a symbol. Okay, we cannot capture the entire circuit. Okay, it will be too tedious and it will not be easily readable. Okay, so we have created a symbol for this, and that has been included over here, just like how we created a symbol in cables. Okay, and then we also created a symbol for R to 2R ladder DAC. Okay, and then we have created a feedback loop. We out DAC to the, and it is connected to the comparator. Okay, so this is how we have designed it. Okay, so let me show the simulation results. Let me run the simulation. So you can see the data. Okay, so the input that is given, okay, these are all from the SAR successive approximation register, and this is the output. age 0 in the sense it is going to get is the initial value, age 0 is the reset, and according to the number of bits, okay, so it will start comparing each and every bit. You have 8-bit data, right? So each and every bit will be compared and you get the output over here. Okay. So due to timing constraints, I wasn't able to explain it even deeper. So maybe in future, if we all meet up together for new sessions, we shall have a detailed review. And meanwhile, if you are looking for any online training programs or internship programs, please do visit our website, okay, uh, intuple.com, okay, and you can visit our trainings tab, okay, visit our training tab and you can check for the programs in all these domains, okay, VLSI, RF and antenna design, electronic circuit design and simulation, ANSYS mechanical, IoT and data science, okay. So in VLSI you can apply for programs on system Verilog, synthesis STU, physical design, UDM, design and verification using Verilog. You can also go for career builder programs. Okay. So please visit our website for further details, and you can also go for RF and antenna design. Okay, so please do visit our website in case of any training requirements, and let me also share our email ID. So let me stop sharing. Okay, so let me share my email ID. In case if you have any queries, you can let me know. Okay, in case if you have any queries, you can reach me out at naveen.shankar at the rate of duple.com. Okay, and you can also uh, reach me out at my mobile number. Okay, so I've given all my details. So thank you all. Thanks for your patience, and please do give me your feedback. You can unmute yourselves and let me know your feedback, or you can type your feedback on the chat. In case if you have any queries, you can let me know.
Participants, if you have any doubts or queries, means you can ask. You can post your question in chat box or else unmute yourself and ask the resource person. Your mic was enabled now.
So Kumash sir wants to discuss with me about a project in agriculture. Definitely, sir, you can always reach me out. Anything else? So Rasik Patel, nice session. Thank you, sir. Thanks for your feedback. Anybody else? Any other queries? And if you can share your feedback by unmuting yourselves, it would be great. Or you can also give me your feedback on the chat. No issues. Any other
Sir,
queries?
is it possible to apply for patent based on agriculture project? Naveen
Yes, sir.
sir, is it
Yes, sir.
audible?
Yes. Yes, sir. You are audible, sir.
Sir, I am GS Uday from St. Joseph Institute of Technology.
Okay.
Is it possible to apply patent for agriculture related projects?
Yes, sir. You can apply.
Yes, sir. Okay, okay. I will talk you later, sir. I noted your mobile number. I
Sure,
will
sir.
call you later.
Okay, sir. Sure.
Okay. Thank you, sir. Thank you.
Yeah, thank you. Anybody else? Any other queries or feedback? Any assistantship provided for research scholar? What kind of assistance is required, sir? So you have to let me know about that. Only then I can tell whether it is available or not. Okay, we can provide you assistance on tool part. Okay, in case if you are facing some issues on the tool side, we can help you out. Otherwise, you can in with your design, okay, you can reach out to us, but it also depends on the availability of engineers, okay, because we are academic channel partners for colleges all over India. So in case if any one of our engineers are free, or if you have raised your request, then at least some 10 to 15 days in advance, then we can plan a one-on-one discussion, okay, and we can provide you assistance on your project. And it will be coming as a consultancy kind of thing. So in case sometimes you may also be required to pay for the sessions. Okay. Hope I answered your query, Pawan Kumar sir. Did I answer your query, sir? Anybody else? Any other queries? Uh, Sir, providing cadence tool is based on which domain you are working on. We provide the tools for digital domain, like Incisive, Incisive, Innovus, Tempus, Voltus, Genus. So those tools we are providing right now. And you can raise your query. You can write memory circuits in the sense whether you are using transistors for the design or you are using any standard cells. You are writing a very long program. Anything we can do it in both aspects, right? So you have to let me know about that. Transistor based. Right now we have some technical difficulties on analog tools. So anyway, you can write to me on my email ID so that I can check with my higher ups and get back to you. Yeah, sure, sir. You can reach me out personally. Yeah. Any other queries, participants?
I think there is no more queries, sir.
Okay. Okay.
Let
Thank you
me
all.
wind up, sir.
Yeah. So
Yes.
any feedbacks? So if you could unmute yourselves and give me your feedback, it will be great. Or you can also type your feedback on the chat. Thank you, sir. Thank you, Pawan sir. Anybody else? Okay. Thank you all. Thanks for your time and thanks for your patience. Yes, sir. We can wind up the session.
Yes, sir. The farmers don't work till the sun goes down. They work till the job gets done. This way, our resource person convey his speech from morning to evening until that cadence to practical session will complete. So in this way, now I'd like to thank our today's resource person, Mr. J. Navin Shankar, Field Application Engineer, Interpol Technologies, for providing this wonderful practical session for using a Cadence ATA tool. On behalf of organizing team and Governor College of Engineering Technology, I'd like to once again thank you so much, sir.
Yeah, thank you. Thank you very much.
Thank you. Participants, the day 10 session 2 attendance and the feedback link is posted in chat box. Kindly check it. Thank you all.